In this video, we're going to look at what happens if you have a current loop in a magnetic field, and this is discussed in chapter 30-13 of the textbook. Okay, so imagine a current loop, and for simplicity, we're going to imagine a square current loop for the moment. So here we have a current loop, so we've got a current that's traveling sort of in a clockwise direction. You can see the little current labeled here. And if you go through, well, these are wires in a magnetic field, so there's going to be a force. If you use the cross product and you figure out the direction, so the forces on each one of the individual sides are shown here. So on the bottom side, it's pointing down, the right side, it's pointing to the right, and so on. So, well, if you think about all these forces, well, if you take the net force, well, the net force is actually going to be zero, because we've got a force that's up and down and left and right. So if we add all those forces up, the net force on our current loop is zero. However, it still is going to experience a torque. So if you look on the right here, so this is now kind of a top view. You're looking down at the top of this current loop. So there's going to be a force on the bottom part that's pointing down, a force on the top part that's pointing up. And if you pull in those directions, it's actually going to cause your current loop to rotate. So it experiences a torque, and if you work it out, so you can actually find that the torque on our current loop is equal to the magnetic moment, mu, cross product with the magnetic field B. Or the magnitude of the torque is, well, I times A is the magnetic moment times B times the sine of the angle in between them. So this also means that the current loop is going to have a magnetic potential energy. So it actually wants to rotate until it minimizes that potential energy. So it actually wants to align until this magnetic moment of your current loop is actually aligned with the field lines. Now, of course, well, for simplicity, we did this for a square current loop, but it actually works just as well for a circular or any shape current loop. All right, and the potential energy is related to mu dot product with the B field. Excuse me. Now, so if we can make a current loop rotate, we can actually use that to build a motor. So imagine, so you take a current loop, well, in practice, you usually loop around several times. So there are actually many loops. You put that in a magnetic field, but of course, since the torque is only in one direction, what we need to do is we need to actually flip the current every half turn, and that actually changes the direction of the torque, excuse me, which means we can actually, if we do that, we can actually cause our little current loop to spin continuously. And that's what we need to build a motor. And in practice, a common way to do this is with something called a split ring commutator. So it's really just a ring that's split on either side, and you have some connections to the ring. It's often called a brush. So that's actually touching this ring, and basically the brushes are in a fixed position, so then when the ring actually starts to spin, every half turn the brushes are actually touching the opposite sides of the ring. So the current gets reversed, and then it'll just spin continuously. And this is nice because this generates a continuous torque. So you can actually use this for a motor to spin things, whether it's a drill or anything that generates a spin.